Hello, my dear students. Keep learning wherever you are. Our subject is operations research, and today's our topic is linear programming problem. We are going to learn about linear programming problem and its formulation, how the real life problems are converted into mathematical form. Okay, for that we have to convert any problem into linear form of equation. Okay, in less than or equal to, greater than or equal to, or in equal to form, but the equation should be in linear form. Okay, so general mathematical model of LP. This is the general formulation of linear programming. Before that, we have to take some assumptions in LP, linear programming. It is founded by George Denzin. Okay, and the assumptions are proportionality, non-negativity, continuity, additivity, and certainty of coefficient. Okay, this is the general form of, or you can say general model of linear programming. Okay, optimize, that means you whatever the our objective is, either it is of maximization or minimization. Means suppose it is a profit, then we have to maximize it, and suppose it is a cost, then we have to minimize it. So it depends on the problem. So optimize, maximize or minimize z is equal to c1x1 plus c2x2 plus up to plus cnxn. Okay, here x1, x2, x3, xn are called as decision variables, on which variable we are taking decisions. Suppose we are earning profit from x product, that is x1, from y product, that is x2. So this will give the decision. So these are the called decision variables, and all these decision variables are constraint, means limitations. Okay, these are written as subjected to linear constraint, that is x a1 x1 a11 x1 plus a12 x2 plus up to plus a1 xn. It should be less than or equal to, greater than or equal to than b1. Okay, the in equation is linear, but it should be less than or equal to, greater than or equal to, or equal to. Another constraint, a21 x1 plus a22 x2 plus up to plus a2n xn less than or equal to, greater than or equal to, or equal to b2. Okay, here there are number of constraints, there are no limitations for constraint, there are no limitations for decision variables. Okay, and last, x1, x2, x3, xn, all the decision variables are non-negative, that is greater than or equal to 0. Okay, now next is LPP formulation, linear programming problem formulation. These are the basic steps of linear programming problem formulation. To apply LP technique, it is required to formulate the LP problem from the given conditions. Following are the steps of the followed by the formulation of LP problem. Step number 1, that is identify the decision variable and express them in terms of algebraic symbols. Okay, whatever the problem is, from that problem you have to identify from on which basis we are taking decisions. So, and give them symbols, so like x1, x2. Okay, alpha 1, alpha 2, you can take any symbol. Then step number 2, so step number 1 is identify the decision variable. Step number 2, identify the objective function which is to be optimized, that is or maximization or minimization, and express it as a linear function of the above defined decision variables. Okay, you have to identify objective function on which basis you are considering the whole equation. Means either you are going for profit, then you have to maximize it, and you have to convert it into decision variable form, whatever the symbol you use. Okay, later on you will learn in example clearly. Okay, so express it a linear function of the above defined decision variable. That is step number 2. Now step number 3, identify all the constraints. Constraints means limitations. Okay, you have to work in limited resources. So identify the constraint, whatever the limitations are, and that you have to convert into linear form. Identify all the constraints or limitations in the given problem and then express them as a linear inequalities or equations in terms of our defined decision variables. In every equations or in every constraints you have to use now decision variables. And step number 4, express the decision variables as feasible variables. That is, all decision variables are greater than or equal to 0. Okay, here all decision variables should be greater than or equal to 0, because suppose you are taking considering as a production allocation problem, you cannot produce any product in negative form, means minus form. So that is one example. So you have to consider all decision variables that is feasible, so it is all equal to greater than or equal to 0. Now we are taking one example. Let us take an example. Okay, now suppose the example is like this. A firm produces three products are proceed on three different machines. The time required to manufacture one unit of each of the three products and the daily capacity of the three machines are given in the below table. Okay, table is given here. Okay, the problem is they are manufacturing three products on three different machines and the machining time are given. Okay, now it is here, you can see here there are three machines, three products. Okay, and machine 1 and product 1, they for machine 1 product 1 they are considering 2 minutes and processing time, and for machine 2 they are considering 4 minutes, and for machine 3 they are considering 3 minutes. Same for product 2, M1, that is machine 1 is taking 3 minutes, M2 is not processing on product 2 is not processing on M2, and M3 is taking 5 minutes. And machines daily capacity, so see, you can see M1 capacity is 440 minutes per day, M2's capacity is 470 per day, and M3 machine 3's capacity is 430 per day. Now this is the data given to you. It is required to determine the daily number of units to be manufactured for each product. The profit per unit for product 1, 2 and 3 is rupees 4, 3 and 6 respectively. Means that profit per product, means for product 1 the profit is 4 rupees, for product 2 profit is 3 rupees, and product 3 profit is 6 rupees per product. Okay, and we have to determine how many products we have to produce. For product 1, 2 and 3, it is assumed that all the amounts are produced are consumed in the market. Formulate the mathematical model that will maximize the daily profit. Okay, so formulate the mathematical means linear programming model that will maximize the daily profit. This is the problem. Okay, problem, what the problem is, there are three machines, there are three products. Okay, and their process time and machines daily capacity are given. Okay, and per product profit is also given. So we have to calculate how many products we have to produce for maximum profit. Suppose the for product 1 we are profiting 4 rupees per 4 rupees per product, for machine 2 3 rupees per product, and for machine 3 6 rupees per product. So how many product we have to produce from all these three machines that we can get maximum profit. Okay, and it is assumed that all amount produced are consumed in the market, means whatever the product you are producing, that is consumed in the market or sold in the market. Okay, now let us start. First of all, as per our step number 1, identify the decision variables. Here how we can take decision by, the number of product produced for product 1 2 3. Suppose let us assume that from machine 1 and 2 and 3, product 1 2 and 3. Okay, so we are producing x1 product for product 1. Okay, product 1 we are producing x1 product 2 we are producing x2 product, and product 3 we are producing x3 product. Okay, so these are called decision variables because we have to maximize it. We don't know how many product right now is, but we know that for product x1 profit is 3 rupees per product. Okay, and for product 2 profit is 4 rupees per product, and for 3 profit is 6 rupees per product. Okay, now so x1 x2 and x3 are called decision variables. Okay, now we have to identify the objective function. Objective function means here we are going to maximize the profit, so it is problem of maximization. Maximize z is equal to, for product 1 we are considering x1, and for one product it is 3 rupees, so we are assuming that 3x1 for product 1. For product 2 that is 4x2, and plus for product 3 that is 6x3. So we have to maximize all these 3 products, and we have to consider it is a maximization project. Okay, now it is subjected to means the constraints here 3 machines, so we have 3 limitations, 3 constraints. 1 2 and 3 means machine 1 you cannot run machine 1 more than 440 minutes per day, and machine 2 for 470 minutes per day, and machine 3 for 430 minutes per day. So here the constraints are given, you have to formulate it into equation form or less than or equal or greater than or equal to type of a form. So see here, constraint for machine 1, that is 2. Suppose we are considering 2 for product 1, machine time is x1 and product is x1 for machine 1. So product we are producing x1 product, so 2x1 for machine 1, for 3x2 because we are producing x2 product right now as per the decision variables, 3x2 plus 2x3, but all these 3 products time should be machine capacity, means 440, it should not exceed 440, so it is less than or equal to 440. This is your constraint number 1. Same for machine 2, this is for machine 1, same for machine 2, that is 4x1, and on machine 2 product 2 is not processing, so 4x1 plus 3x2 less than or equal to 470, and for machine this is for machine 2, and for machine 3 2x1 plus 5x2, and it is not works on a machine product 3 is not works on a machine 3, so it is less than or equal to 430. So here is a constraint number 1, here is a constraint number 2, and here is a constraint number 3. These are the limitations for to achieve this objective, that is 3x1 plus 4x2 plus 6x3. And last step is all the decision variables are greater than or equal to 0, means non-negative, that is x1, x2, x3 greater than or equal to 0. This is our formulation for the above production allocation problem. So this is our solution, okay, for the problem. Now to solve these types of problem, there are different methods like graphical method for two decision variables, simplex method, big M method, two-phase method, okay, that we are going to learn for further in lectures. Okay, thank you.